Prime numbers are the fundamental building blocks of all whole numbers, a concept that has fascinated mathematicians for thousands of years. Think of them as the atoms of the number world. A number is called prime if it is greater than 1 and can only be divided by itself and the number 1. For instance, the number 7 is prime because its only divisors are 1 and 7. However, the number 6 is not prime, as it can be divided by 1, 2, 3, and 6. These non-prime numbers are called composite, and they can all be broken down into a unique product of primes. It is this foundational role that makes primes so captivating and essential to the structure of mathematics. For centuries, the primary method for determining if a number is prime has been through a process of trial and error, specifically through division. To test if a number, let's call it n, is prime, one would systematically try to divide it by every integer from 2 up to the square root of n. If none of these divisions result in a whole number, then n is declared prime. This straightforward process works perfectly for smaller numbers like 29 or 53. But when we start dealing with numbers that have hundreds or even thousands of digits, this method becomes incredibly slow and impractical, even for the most powerful computers we have today. This computational difficulty is not just a theoretical problem, it has profound real-world consequences. The apparent randomness and the difficulty of factoring large numbers into their prime components form the very backbone of modern digital security. The encryption that protects everything from your online banking transactions to your private messages relies on this principle. Essentially, we create locks that are easy to make using 2 large prime numbers, but almost impossible to pick without knowing those specific primes. This makes the study of prime numbers not just an academic pursuit, but a cornerstone of our secure digital lives, driving a constant search for deeper understanding. The quest to understand primes has led to some of the most famous unsolved problems in mathematics, such as the twin prime conjecture, which posits there are infinitely many pairs of primes that are only 2 apart, like 11 and 13. Their distribution seems to defy any simple pattern, making them appear scattered almost randomly along the number line. This has led many to believe that primes are inherently chaotic. Yet, the search for an underlying order, some hidden structure that governs their placement, has never ceased. The idea that there might be a secret logic waiting to be discovered continues to inspire mathematicians around the globe. While the study of primes focuses on multiplication and division, another area of mathematics, called combinatorics, explores numbers through addition. This is where we encounter the concept of an integer partition. An integer partition is simply a way of writing a whole number as a sum of other positive integers. The order of the numbers in the sum does not matter, so we are only interested in the unique combinations. This simple idea opens up a surprisingly rich and complex world of numerical relationships, offering a completely different lens through which to view the integers that we thought we knew so well. Let's take a simple example to see this in action. Consider the number 4. We can ask ourselves, in how many different ways can we write 4 as a sum of positive integers? We could write it as just 4 itself. We could also express it as 3 plus 1. Another way is 2 plus 2. We can break it down further into 2 plus 1 plus 1. Finally, we can write it as the sum of ones, 1 plus 1 plus 1 plus 1. In total, we have found 5 distinct ways to partition the number 4. Each of these unique sums is a partition, and together they represent all the additive combinations that make up the number. To keep track of this, mathematicians use something called a partition function, often denoted as p of n. This function simply counts the number of partitions for any given integer n. So for our previous example, we would say that p of 4 equals 5. As the numbers get larger, the number of partitions grows incredibly quickly. For example, the number 10 has 42 partitions, and the number 100 has over 190 million. This rapid growth makes partition functions fascinating objects of study in their own right, with deep connections to other areas of mathematics that were first explored by the great mathematician Leonhard Euler in the 18th century. For a very long time, the world of prime numbers, which is rooted in multiplicative properties, and the world of partitions, rooted in additive properties, were seen as entirely separate fields of study. There seemed to be no obvious connection between them. Primes were about what you can't divide a number by, while partitions were about how you can build a number up through addition. The idea that these two fundamentally different ways of looking at numbers might be linked by some hidden law was not something that mathematicians had seriously considered until a recent and groundbreaking discovery changed everything. The incredible breakthrough came from a team of mathematicians who found a previously unknown connection between prime numbers and integer partitions. They discovered that it is possible to define whether a number is prime not by testing its divisors, but by seeing if it satisfies certain equations built from partition functions. This was a monumental revelation, as it created a bridge between two domains of mathematics, multiplicative number theory and combinatorics, that had long been thought to be completely independent. It suggested that the nature of prime numbers was far more structured than anyone had previously imagined. This new method provides a completely different way to check for primality. Instead of performing division, we can now plug a number into a specific type of equation, known as a polynomial. These equations use the values from partition functions as their coefficients. If the number makes the entire equation equal to 0, then n must be a prime number. If the result is anything other than 0, the number is composite. This is a radical shift in perspective. It redefines what a prime number is, framing it as a solution to an algebraic equation rather than as a number with specific divisive properties. To illustrate with a simple conceptual example, imagine an equation like, say, some coefficient plus another coefficient equals 0. The coefficients in the real equations are complex, but the idea is the same. The coefficients are derived from partition functions. Let's test the number 5. We would calculate the required partition values related to 5, plug them into the equation, and see if the result is 0. Because 5 is a prime number, the equation would balance perfectly. Now, if we were to test the number 6, the calculation would yield a non-zero result, telling us that 6 is composite. This algebraic test offers a definitive yes or no answer without ever performing a single division. What makes this discovery even more profound is that the researchers proved there isn't just one such equation. There are infinitely many of them. They have uncovered an entire family of polynomial equations that can be used to identify prime numbers. This suggests that the connection is not a mere coincidence, but a deep structural property of numbers. The finding implies that the seemingly chaotic distribution of primes is governed by a hidden order, an order that can be expressed through the language of partitions. It's a clue that the randomness we perceive might just be a reflection of a pattern we had not yet learned to see. The discovery of this link between primes and partitions has sent ripples throughout the mathematical community. Its primary importance is theoretical, as it offers a fundamentally new lens through which to view the oldest and most mysterious objects in number theory. For millennia, we have defined primes by what they are not. They are not divisible. This new finding gives us a positive definition, defining them by a property they possess. They are the solutions to a specific class of equations. This opens up entirely new avenues of research and allows mathematicians to ask questions that were previously inconceivable about the nature and structure of numbers. While this new method is not yet faster than existing prime testing algorithms for practical purposes, its implications for the future of cryptography are significant. Our current digital security infrastructure is built on the difficulty of factoring large numbers, a problem intimately tied to primes. Any new insight into the fundamental properties of primes is therefore of great interest to national security agencies and technology companies. As we move towards an era of quantum computing, which threatens to break our current encryption standards, a deeper and more varied understanding of primes becomes absolutely critical for developing the next generation of secure communication. This breakthrough might also inspire similar discoveries in other areas of mathematics. If a hidden relationship existed between primes and partitions, two seemingly unrelated fields, where else might such connections be hiding? It encourages mathematicians to look for surprising links between different branches of their discipline, fostering a more holistic approach to solving long-standing problems. The work may inspire further investigations into the hidden algebraic or analytic properties of other combinatorial functions, potentially unlocking more secrets that have been hidden in plain sight within the vast landscape of numbers. Ultimately, this discovery reminds us that even in a field as old as mathematics, there are still profound mysteries waiting to be uncovered. The prime numbers, which have been studied since the time of Euclid, have revealed a new layer of their identity, suggesting they are not just a random sequence, but possess an elegant internal structure. It shows that there is a deep and intricate pattern woven into the fabric of our number system, a pattern we are only just beginning to understand. The journey to fully comprehend the world of primes is far from over, and this new map promises that there are many more exciting discoveries yet to come.